Okay, let's get started talking about radiation again. So, thank you all for being here. It's Monday of Thanksgiving and we don't have class tomorrow. So, we're going to finish talking about radiation today and Wednesday. Class is canceled tomorrow, but I will post recitation problems, and if you have questions about them, I'm happy to take some lecture time to go over them. And then we'll assign the last homework on Wednesday. That will be due the following Wednesday. I'm expecting this one to be a little bit shorter because there's like Thanksgiving and it's the last dead week. It's due on dead week, and we're covering kind of a smaller amount of radiation compared to the other topics that we've gone through. Any questions about kind of the logistics of finishing up? All right, and so then for the final exam, we'll just I won't test you on anything that we have not had homework over. So the last week of lectures, we'll probably just do a couple additional things of radiation that I think are really interesting, stuff that I want to kind of tell you that is really interesting about radiation, but that I won't specifically ask you homework problems on or test you on. And then maybe do example problems on the last day instead of lecture. We'll see. Okay. So that's kind of what the rest of the quarter is going to look like. So on Friday, we introduced the concept of spectral intensity. And that was this I sub lambda E. And we basically said this is the rate at which radiant energy is emitted at a specific wavelength in a specific direction per unit area of the surface normal to this direction, per unit wavelength, per unit solid angle. And then we said we can integrate this up over all of the directions to get the spectral emissivity, and then integrate that up over all of the wavelengths to get the total emissive power. So we went through that for emission, and then we repeated it for irradiation and radiosity. And then finally we said to actually calculate any of these fluxes, the emission, irradiation, radiosity, we need to know what the spectral intensity is. And to calculate that, we use the concept of a black body. So we just started talking about black bodies and wrote down a few properties of black body radiation. So we said black bodies absorb all incident radiation. This is stuff you should already have. For a given temperature and given wavelength, no surface can emit more energy than a black body. And finally, black bodies are diffuse emitters. So the emitted radiation of a black body is independent of direction. And so we wrote down, for the spectral intensity, we wrote down kind of these special expressions for diffuse emitters. So for black bodies, those are the expressions that you'll use. Okay, so we're going to finish off talking about black body radiation today, and then maybe get into radiation exchange between surfaces. Okay, so we'll say black body radiation continued. So we said black bodies are idealized perfect absorbers and emitters, and so they serve as a standard against which real surfaces are compared. And we talked about that a little bit when we first introduced radiation and introduced the concept of emissivity. So a black body does not actually exist, but it can be very well approximated by a cavity whose inner surfaces are at a uniform temperature. So that's kind of the closest we'll get to seeing a black body as a real surface. And one of the most useful properties of a black body is the fact that its spectral intensity is just known. It's been characterized and so since it's known, we can express the spectral intensity of real surfaces in terms of the spectral intensity of black bodies. So the spectral intensity of a black body is known. And here this is lambda sub b to show that this is black body spectral intensity. And we typically write the spectral intensity in terms of the wavelength and direction, but because black body emission is diffuse, we're just writing it in terms of the wavelength and temperature here. So the spectral intensity of a black body is 2h c sub naught squared over lambda to the fifth times the exponential of h c sub naught over lambda kb times t minus 1. And this h, k sub b, and c sub naught are all constants. So h is 6.626 times 10 to the negative 34th joule seconds. KB is 1.381 times 10 to the negative 23rd joules per K, per Kelvin. And C sub naught is the speed of light in a vacuum, which we wrote down, I think, last week. And then important to note that T is absolute temperature, so it needs to be in Kelvin, which is typically the case dealing with radiation. As we said, a black body is a diffuse emitter. So from last week, we wrote down that for diffuse emitters, the spectral emissivity is just equal to pi times the spectral intensity. because the intensity of radiation is the same or even in all directions. So the spectral emissivity is just pi times this expression here. This is known as Planck's law. So the next step after calculating spectral emissivity typically is to calculate the total emissivity, so integrate up over all of the wavelengths. So we can do that for a black body. So the total emissive power is the spectral emissivity integrated over all wavelengths so again, it's just pi times the expression for the spectral intensity. And then since these constants are all known, we're just integrating in terms of lambda from 0 to infinity. So the only variable that we'll have left is the temperature T. So performing that integration, we get the familiar expression for the emissive power of a black body as sigma times T to the fourth. So that's where this expression comes from that we first introduced when we talked about radiation. So it comes from the spectral intensity of the black body. It's diffuse, so we don't have to specifically integrate over the directions. And then we integrate over all the wavelengths, and that gives us sigma T to the fourth. Yeah.
In the text, I know they're using these like radiation constants.
Yeah, C1, C2, yeah.
Right. It looks like they're just kind of grouping things that are used that come together a lot.
Exactly.
Right?
Yeah.
There's
Yeah.
no like meaning beyond it. They just happen to show up mathematically together a lot.
Right.
Okay.
Yeah, there's no additional meaning. So he's referring to, in the text, they present these equations and kind of group some of these constants, like H and C sub naught, and I think maybe,
The whole numerator there is like the first constant actually.
yeah, the whole numerator, okay. And then they have it as like capital C sub naught is one constant, and then there's another constant, C sub 1, that shows up in the bottom. And yeah, you're welcome to use those. I just didn't write them specifically because it's a little redundant to write out more constant expressions. Yeah. Okay, so this we said before, sigma is 5.67 times 10 to the negative 8th watts per meter squared K to the fourth. And that is the Stefan-Boltzmann constant. And then this equation, E sub b is sigma t to the fourth is the Stefan-Boltzmann law. And it gives the radiation emitted by a black body per unit surface area in all directions over all wavelengths for a certain temperature. And then again, we said emission is diffuse. So from the expressions that we wrote down on Friday, the total intensity of a black body is going to be just the total emissivity divided by pi. So I think we probably wrote down just that the total emissivity was pi times the total intensity.
Is the emissive power then essentially the same as like the surface flux?
It's the same as the emissive surface flux.
Right.
The same as the emission. Yeah.
Right. Okay.
Yes. Yeah. Yeah, so capital E is the emissive power or the surface flux due to emission. Yeah.
Okay.
And it's only a surface flux for materials where emission is not volumetric.
Okay.
Yeah.
Right.
Okay. So black body radiation is well characterized, and like we said, it's diffuse, but it does emit radiation over a range of wavelengths. And you can calculate the fraction of total emission that is within a certain wavelength band, which is sometimes useful to be able to do, as the fraction that is between wavelength 0 and lambda sub 2, so the end of the band that you're interested in, minus the fraction between 0 and lambda sub 1, the beginning of the band that you're interested in. And there's a table in the book that has all of these wavelength bands calculated up for a specific value of lambda and t. So for specific lambda times t, basically it says how much of the frequency is within that wavelength band. So useful to be able to use this table to know kind of how much radiation is between maybe at the bottom 10% of the wavelength band or the top 10% of the wavelength band. And another useful thing that is included in the table is the intensity, the black body intensity, divided by sigma times t to the fifth. And so if you have a specific value of lambda times t, instead of calculating the big expression that we wrote down here for the intensity, you can just take the value in the table and multiply it by sigma times t to the fifth to get the intensity. And of course you can interpolate between these values of lambda times t. So the fraction of total emission from a black body that's in a certain wavelength band that's f of lambda sub 1 to lambda sub 2, where lambda sub 1 and 2 are the start and end wavelengths that you're interested in. So you can calculate that as the fraction that's between 0 and lambda sub 2 minus the fraction that's between 0 and lambda sub 1. Where these values are given in table 12.2. And I'll put that on Canvas. So if you look at the reason the table is presented like that, we'll skip down to this real quick. If you look at the original definition of the intensity, so these are constants h, c sub naught, and k, and then lambda and t are the only kind of dependent variables that are still in the expression. And the table is just presenting it as for a given value of lambda times t, because that's a convenient way to present it, even though lambda times t doesn't specifically appear in the equation. But basically because it's listed for such a large range of lambda times t and you can interpolate between the values, it's just a convenient way of kind of expressing those values in the table. Okay. And then we said the table also provides a quick way to calculate the intensity. For a given value of lambda times t. And that's just this value in the third column, multiplied by sigma t to the fifth. Okay, that's all we're going to talk about for black body radiation. Any questions so far? So like we said, we're going to use the characteristics of black body radiation, the fact that it's known, to talk about emission from real surfaces. So we're going to do that in terms of the emissivity, which we have introduced previously. So this should be just a little bit of a review, but kind of introducing it now in the context of the additional information that we know about radiation and black body radiation. So real surfaces emit less radiation than a black body at the same temperature. And we defined previously the emissivity, which is the ratio of the radiation emitted by a real surface to the radiation emitted by a black body. At the same temperature. So the emissivity that we've talked about and used previously is the total emissivity, but because radiation is spectral and directional, you can define the emissivity of a surface for a certain wavelength and a direction. So you might have, for a given real surface, it emits, 95% of the power of a black body in this one certain wavelength and direction, but in another wavelength and direction, only 10% of the emission of a black body in that given wavelength and direction. So we'll just say we can define emissivity for a certain wavelength and direction. So the same surface could have many different values of emissivity depending on the specific wavelength and direction you were talking about. But we're just going to consider total emissivity, so that's the integrated average over all of the wavelengths and directions. So now it's only a function of temperature rather than being a function of the wavelength and direction. So that is the total emissivity is just the total emissive power of a real surface divided by the total emissive power of a black body at that same temperature. So if we rearrange to solve for the total emissive power of a real surface, and bring in the Stefan-Boltzmann law, we get back to this expression for the total emissive power of a real surface as a function of the emissivity times sigma times t to the fourth, which we introduced back when we first introduced radiation, but now you hopefully have a little better idea of where this equation comes from and the derivation of it. Okay, any questions on that? Okay, so we're going to start kind of the slightly more practical application of radiation now. So we've been doing kind of a lot of theory, a lot of definitions and derivations. So really what we're interested in is how much radiation is exchanged between two surfaces. And the amount of radiation depends on a lot of things. So basically the geometry and orientation of the surfaces and their radiative properties and their temperatures. And so the first thing we're going to talk about is how the geometry and orientation of the surfaces affects how much radiation is exchanged between them. And that's determined by calculating this parameter called the view factor. So that's what we'll start on now. So radiation exchange between surfaces. And this will allow us to actually calculate the rate of radiation transfer, so the Q, between two surfaces. So the amount of radiation exchanged between two surfaces depends on the surface geometries, their orientations relative to each other, of course, their specific radiative properties and temperatures. So to simplify this, the first thing we're going to do is just assume that the surfaces are separated by a non-participating medium. So the only perfect non-participating medium is a vacuum, so lack of a medium. But a lot of gases also approximate a non-participating medium fairly well. So that means that they don't absorb any of the radiation between the two surfaces, they don't scatter it or reflect it in any way, and so you can just assume that all of the radiation that is leaving one surface is reaching the second surface kind of in the same manner as it left the first surface. So we'll assume radiation passes through a non-participating medium. So that could be a vacuum or just gases. And then we will account for the surface geometry and orientation with the view factor. Which is capital F sub ij. So the view factor is defined. So it's the fraction of radiation that's leaving a surface I that is intercepted by a surface J. Okay, so to come up with an expression for the view factor, we're first going to consider two kind of arbitrarily oriented surfaces, a sub I and a sub j, that are just at a random distance and angle and orientation compared to each other. So because radiation is emitted in all directions, basically to have a second surface that captures all the radiation from the first surface, it would have to be essentially the hemisphere that we talked about, encompassing the first surface in all directions. So most of the time, when radiation is emitted from one surface, it's intercepted by kind of a complicated array of all the different surfaces around it. And, just even in this room, we're all emitting radiation and it's going in all different directions, and some of it is being absorbed by our neighbor and some of it is going up to the ceiling. So usually just a small fraction of the radiation emitted by a certain surface is intercepted by another surface of interest. So we'll take two random surfaces, and we're going to consider differential areas on those surfaces. Those differential areas are separated by a distance r. So these are we'll draw the surface normals. So this is surface A sub I and A sub j. And the normal, so the direction perpendicular to the orientation of surface I in sub I. And then again for surface J in sub j. And the orientation of the surfaces is defined based on their angle relative to the normal. So theta sub I and theta sub j. And they're at specific temperatures, T sub I, T sub j. And then the differential element that we're considering on each surface, dA sub I, dA sub j. So we're going to consider first just the differential areas. On these surfaces. We said these areas are connected by a line of length r. That forms these angles, theta I and theta j, with the surface normals. And the specific values of r, theta I, and theta j depend on the exact position of the differential area. So if you were considering the differential area over here rather than over here, for example, the specific value of r, theta I, and theta j would change depending on the exact location on the surface. So the values of r, theta I, and theta j depend on the exact position of dA sub I and dA sub j. On the surfaces. So unsurprisingly, we're going to come up with an expression for just these differential areas, and then we're going to integrate over the entire area, a sub I and a sub j, to get a general expression for the v factor between the entire two surfaces. Okay, so let's bring back our definition of the spectral intensity. So remember we said this was the rate at which radiation is emitted from this surface, a sub 1, in a specific direction, wavelength, all those things. So we're interested now in how quickly the radiation emitted from this surface, a sub 1 or a sub I in our case, is intercepted by a sub j. So we're going to modify this equation to be relevant for the problem that we're looking at. So how much is emitted by I and intercepted by j. So we're interested in the radiation over all lambdas leaving the differential area I by emission and reflection, because we're interested in the total radiation exchange. So how much is being emitted and reflected And then we're still just looking at, right now, the specific direction. And how much of this is intercepted by the other differential surface area. So we're considering the total intensity now. So rather than the spectral intensity, the total intensity. So no more dependence on lambda, because we've kind of integrated up over all of the lambdas. And so this is the total radiation, so leaving by emission and reflection. So this is the, going back to the section where we wrote down the spectral intensity for radiosity. So this is the total intensity due to emission and reflection for surface I. And now we're looking at the rate of heat transfer, or the rate of radiation transfer between I and J, so from I to J. So that's what this subscript D, dq I sub j, or I to j indicates. And now our emitting surface, A sub 1, is A sub I. And instead of cosine theta, we have cosine theta sub I. So the relevant angle is theta sub I, that angle with the normal. And then we've removed our dependence on wavelength, so we don't have the d lambda in there. And that's kind of taken care of by the fact that instead of the spectral intensity, we're talking about the total intensity. And then the relevant angle is this angle, this solid angle, d omega j to I, that the radiation passes through when it's moving from I to j. So this is the total intensity leaving I by emission and reflection. And this d omega j to I. Is the solid angle through which the radiation passes. Okay, so on Wednesday we'll finish talking about the V factor and continue this derivation. And then, like I said, no class tomorrow, but you're welcome to come use the room and work on your lab if you like.